I'm myself Ritu Das. I'm an associate professor at University of Michigan, and I work on a lot of different things, but in-memory computing has been one of my very favorite research topics starting around 2016 or so. We started the first line of research on in-SRAM computing. That's where we started here. And in an earlier life, I came here 8 years ago to teach the summer school, and then I was teaching network on chip. So I had a background in interconnection networks, moved on to memory systems, and most recently I'm working on genomics and precision health. So if you like to learn about those, feel free to chat with me during the coffee breaks or lunch and so on. But today's class will focus on in and near memory computing. So just to give you a little bit of an idea how the week is going to progress, I know this is the most boring slide to start with, but it's important just so that you know what's coming up. So today is going to be introduction, basics, setting up the motivation for this research area, right, and understanding some little bit of how memory works, modern memory works, right. And then we move into the way I've organized the class is different layers of memory hierarchy or different memory technologies. So we start with static RAMs, on-chip memory, caches, and so on. And then we move to dynamic RAMs, DRAM, the main memory, and we have 2 lectures for DRAMs, part 1 and part 2. Part 1 would be focused more on near memory computing, so more like traditional PIM, and then part 2 would be more focused on more out there in memory computing with DRAMs. Then the last lecture would be with non-volatile memories like memristors or even storage. I'll see if I have time to cover some near storage computing, and we'll conclude. So that would be our, is there some topic which is missing here which you would like to learn about? Or like, is there a wish list from the class? Anyone? I want this to be interactive. Don't be shy. Ask as many questions as you want. It's supposed to be a fun, like a research class, not like your undergraduate class, right? So, yeah.
So lecture 1 to 4 is how we do today, and 5 is how we will do tomorrow.
No, not well. All the 2, 3, 4 are all like state-of-art research. So this is not just how we do today, but like proposals for future.
Okay.
Yeah. And the last one too, it's different memory technologies. That's how they have been divided. Yeah, okay. But once we get through one, you would probably follow what will come up in everyone. Yeah. Great question. Any wish list? Anything you would like to learn from this class which you had in mind? No? We are all set?
Yeah, I want a bit about how is the computer, what is actually affecting the computer architecture to be able to run directly from
memory,
volatile memories and like that.
Yeah, sure. We'll definitely cover that. That's a great, we'll definitely look at how it works today and how we can make in-memory computing possible. So we'll definitely look into that. Great. Anything else? How about this? I'll ask you this question again towards the end of the lecture, once you have seen a little bit, right? To break the ice. Okay. So let's move on. All right. Class participation, I want more discussion, ask lots of questions. We learn through talking about it. You know, if you don't find anything which is, you know, if you have a question like you don't understand, or you have a question like this doesn't make sense, all of that are welcome. Okay. So let's learn together. Okay. So first, some little bit of motivation for this kind of computing paradigm, which I think is different from conventional computing paradigm. So we have entered a data flood era. So what is data flood? Data flood is the amount of, it's called the data geosphere. So amount of data we are creating, storing, reproducing, okay, every minute. And that data sphere is just, you know, back in 2010, we had about 2 zettabytes of data, and zetta, I don't even want to tell you how much that is. It's a lot of zeros in there. And By 2025, if you see, there's a 90x or 100x, increase in the amount of data we are creating. Why are we creating that much of data? Because of very disruptive technologies which have come about. AI is one of them. We all know how much data is being harnessed by AI, as well as how AI applications are so bottlenecked by data movement, right? So few of the latest models, the foundational models, the footprint of the models is like 500 gigabytes, 500 billion parameters, and so the footprint would be 2 terabytes. To run that out of a computer system, especially the inferences or the training, it's really very memory centric bottlenecks. And the other technologies which we are looking at is all these sensors, smart sensors, IoT, Internet of Things, which are creating lots of data, 5G technology which makes edge data come to the cloud, as well as smart industry solutions. What we see is a lot of automation in industry and manufacturing, that's your industry 4.0, and people are talking about industry 5.0, where we'll have AI plus automation. So all these trends have led to creation of lots of data. And there are a lot of benefits of harnessing data-centric workloads. You can change automation, advances in medical field, even solve environmental challenges like doing climate simulations a lot more effectively. What's the surprising thing is that if you look at this global data sphere today, and this was a statistics from IBM, 80% of this is actually dark data, which is just been collected and archived. We don't know how to process it, and we cannot process it, right? So it's till it is dark, it is actually valueless. So that's our dark data. And another interesting statistics, if you go and find about many different industries like healthcare, media, financial services, manufacturing, they have come up with a metric called data readiness factor, data readiness index, and it is actually 2.4 to 3.3 across all these industries, where 5 is optimized, ready to be used, and 2.4 is actually for the healthcare industry, right? So what we see is that although there's a proliferation of data, we don't really have computing power to harness it yet. So let's focus on data-centric and memory-centric systems. Why so? So here's a logical overview of why, right? So if you think about conventional processing, so I've shown a processor and caches on the left, and then this is a typical memory hierarchy, right? So you have got some on-chip memory, then you have the main memory and storage. We all are familiar with this from our undergraduate classes. And typically the processor is the center of the universe, right? And it goes and fetches data from the memory, disk, and so on, and then all the computing is happening at the processor. Now, if we analyze a bit deeper into where the energy is going, and this is an energy, but it's also proportional to time, 20 to 40x is going in the data movement, in just shuffling the data around from the processor across the whole elaborate memory hierarchy which we have built, right? And very tiny bit of it is actually the ALU operations which we are doing on it, the crunching of data. So clearly we know where the bottleneck is. It is in the data movement here. Now, I'll show you a bit more fine-grained statistics on that, but this was to motivate it. So what is one possible way of addressing this problem? At a very high level, we can do near or in-memory processing, where the processor, how does a processor get data? And it's just not the processor, the GPUs, accelerators, all of them get data in, right? And then only they work on it. How do they do it today? Any ideas? What's the ISA semantics for that? It's very fine grain. Yeah? You have your hand raised, or? Anyone? Yes?
From the resistor,
Mm-hmm.
the sample of the request, goes to caches, cache misses, goes to another caches.
Right.
Goes to the DRAM computers, some 100 latencies back, gets data.
Right.
To the resistor.
Absolutely right. And what is the instruction ISA semantics for that? Loads and stores. That's what I was looking for. Wonderful, right? So loads and stores, right? The processor issuing loads and stores and getting all the data across the memory hierarchy. And that whole pathway which you described, right? So instead of doing loads and stores and getting it all the way to this silicon, right? What we can do is instead we can embed some compute elements in the processor cache. Okay? So now we don't do loads and stores to the cache. The cache itself will process the data, and the reason I asked you to think about loads and stores is now the whole ground has shifted, right? So loads and stores are not going to work. So what the architecture is going to be like, what the programming model is going to be like, how the compilation flow will look like. So keep thinking about that, and we'll address that over the time, right? So interface has to change. Or we could do it in the memory, that would be your compute memory. When I'm highlighting these portions, all I'm saying is you will embed compute logic in them somehow, right? How we embed compute logic, what is that compute logic, we'll learn during the class. But this is just a different spectrum. You can build a compute cache, a compute memory, or even a compute storage. And then in the compute memory, the two flavors here. One is if you have a 2D like DIMMs, conventional DRAMs, then you would, and this is actually from the very early or one of the early works on PIM in 90s, right? They would embed logic right at the periphery of the banks. So that's your 2D. Or you could go 3D, if you have 3D memory systems, then you could embed the logic in the base layer of the memory, right? So you come through TSVs and get to the logic layer. So those are the two flavors in memory, or you could even do it in the computational storage mode. Yeah.
I mean, for doing anything you need a program, so
right.
You're now flooding around the program everywhere. How do you solve that?
How do you solve that? So that's the programming model. We'll look into it. Lecture 2 coming up. Yeah. So bear with me. But that's a great question. You're jumping ahead, so you're already thinking of how to do it. Yeah, one more question there.
With near and in, which do we consider near and which is in? Is in all the way to the left or all the way to the right?
So near and in can be anywhere in the memory hierarchy. So with cache also it can be near or in. With DRAM also it can be near or in. With storage also it can be near or in. And for every layer of memory hierarchy we'll see both the flavors. Yeah. Yes.
So in, for example, the cache thing, there can be a near and in. But the definition for near in computing in process will be kind of vague. But for example, if you have in one place a small hash from like 1 kilobytes and then you have a small processor next to it,
yeah.
Would that be considered near? Then what would we consider as the normal or the...
So I have an exact taxonomy for it. So just hold on. It's coming up in a few slides. We'll precisely define and then we'll come back to your question, right? But it's the way, at least, let's not jump ahead. Just give me 5 minutes. I'm getting to that. The exact precise definition in mind. Look, there's no consistency here in the whole research community, but I'll give you my definition of near versus in, right? Okay. Yes.
The question is about, I mean, the processor is very fast, DRAM is a little bit slower, and SSD
is really slow.
So that means there is a reason why you're moving it also, because you want to use this fast unit to the left.
Yeah, that's such a smart question. So how do you make up for the processor speed, right?
Yeah, so if you're moving around, that means slow things you can do in the SSD maybe. Mm-hmm. So yeah, I'm waiting for you. Probably have the answer.
Yeah, I have. But I'll give you one short answer to it. Parallelism.
Pardon?
Parallelism.
Okay.
So when you go to memory, the memory has lots of internal parallelism, and I'll show you all that. And that's how you make up for the slow speed.
So you're moving the problem to the software guys.
Well, okay. There is a software stack too which can be leveraged like CUDA or others, and I'll show you how we can do that. Yeah. But we are moving it to the software. That's a good point. All right. So these are the different flavors, and excellent questions, all of you. And I'll go to the precise definition of near versus in very soon. But this was just to get you all started. So one thing common among this is what I'm showing you here is an integrated near or in-memory computing, right? So, it's a part of the memory hierarchy and you have embedded compute in it. Another flavor of near in-memory is that you actually build a separate ASIC of in-memory technology, right? So, here you think of it like a GPU replaced by an ASIC. So, it's very different from having an integrated system. So, both flavors exist today in the market, right? But I think this is a bit easier and a more near-term solution before we solve all the software and the interface problems with the integrated hierarchy. That's clearly more useful because you already have that silicon and you can reuse it. This is creating a completely separate memory address space, separate chip, but that's a more near-term solution. So, that's what we see initially going around, and then hopefully we'll get to the integrated accelerators. So, now let's break it down. So, I gave you a very high level picture of why we should do this, but now let's go into a little bit more specifics of why. So, I'm going to show you 3 reasons: energy, bandwidth, area. All these 3 reasons are very important motivation for near or in-memory computing. Energy is somewhat well understood, but people often forget about bandwidth and area. So, first let's take a look at energy. So, this analysis was done by Daly and his students about 8 years or so ago, and what they showed was that communication and memory dominates the arithmetic energy. So, let's look at this at a perspective, right. So, they took a 20 by 20 millimeter square die, okay, and they showed the relative energy taken by all these different things which is going on. So, first thing on the left is just a 64-bit ALU, about 20 picojoules, right, that's 10 to the power minus 12, okay. Then what they showed was an SRAM just accessing one small SRAM bank, SRAM array is 50 picojoule. But then if you look at the interconnection network, right, to go from that end of the chip to this end of the chip, if you had to do that, that's a worst case. So, this blue line here is 1 nanojoule, okay. And then if you look here, right, so we are all going in relative, 20 picojoule is the smallest value on that screen, and then we have 16 nanojoule, which is DRAM read and write energy, right. So, that's a couple of orders of magnitude higher in terms of energy, how much it takes. And so, so it's all relative. So, we are paying, to make the compute more efficient, sometimes we are sacrificing that energy, and also the off chip link is 500 picojoule, right. So, if we do near or in memory computing, what is it that we can save from this slide deck? Anyone? Which energy do we save here? Any thoughts? Yeah? Go for it. Yes, you. Memory access, unfortunately, no, because you still have to access the memory to do in memory computing. But what else? Yes, the data buses, right? So, all the blue lines and that 500 picojoule, that's what we are saving with near and in memory, right? And that's substantial, but it's very important to know that we still have to pay a lot of memory accesses, but a lot of communication energy is what we are going to save, right? Yeah.
Do you have to consume energy for, say, a simple arithmetic like an addition?
Yeah, that's that little green thing there.
Oh, true.
Yeah, it's so tiny, right? Yeah. So, but that's the pure arithmetic, right? When you look at the fetch, the pipeline energy, like the core, out of order core, that's still expensive, but the actual ALU, it's very tiny.
So that's the average, like 20 picojoules for multiplication and
Yeah.
addition average?
Yeah, that's kind of rough order of magnitude there. Yeah, yeah. Yes?
But essentially with this new, can we make a general kind of statement that this near in memory computing will kind of decrease the amount of data transfer?
Right. The data transfer, the communication energy, that's the key energy we are saving. Yeah, yeah, right. Absolutely right. Good. Yes. Yeah, go.
Can you see what is the energy consumption of caches in the world?
Yeah, so SRAM is 50 picojoule here, right? But that's just one memory array. Cache would be the on-chip buses. So you're seeing these 256-bit buses, right? So you go to add that and the SRAM access to think about the total cache energy. Because you never just access one memory array. You have to go through all the interconnects and then go to the cache.
Yeah, the cache is always very big. Big means that it has a lot of energy consumption, especially for static energy consumption.
Right, but you would be surprised, and I'll show you in the next lecture. They are big, but most of that energy is coming from the interconnection. Yeah, the actual SRAM access is very small, 50 picojoules. All of it is coming through that little ring, bus, and all that, which goes to that SRAM array. 90% of it. Yeah. So that you will save if you do compute cache, near cache. Yeah. Yes.
I have a similar question. So when we say that DRAM read write is 16 nanojoules,
Mm-hmm.
is that the cost of accessing a DRAM cell, or is that the cost of going through all the interconnects inside the DRAM as well?
No, just the DRAM, like from the DIMM. So you have reached the DIMM, right? And then you are accessing. That's that energy. So the off-chip net, like the links, that's 500 picojoule right below it.
Right.
Yeah.
So what process is this valid for?
Oh yeah, this is a bit old, right? So they have done it on 45 nanometer. This is
5 nanometer.
45 nanometer.
45,
Yeah, it's really old. But the trends are similar.
And
Yeah.
at which temperature? Because leakage goes up with temperature exponentially. So
That's right. So I think this is at room temperature. They have done the analysis. So temperature is, I mean, we can trust the results in the sense that they have done it for a normal operating environment. I don't know exactly which temperature.
dynamic power.
This is dynamic power, average dynamic power. Yeah, absolutely. But if you look at the reference, HiPEAC 2015, that would give you the details of exactly which temperature and all that they did the analysis on. Yeah, so one more slide on energy, right? So this I was showing about general purpose processing, right? Now, this is one more which they did the analysis on a accelerator architecture for AI, because there we are thinking about addition and multiplication. So this gives you a little bit more idea of the exact operations and the relative of the different memory hierarchies we have. So this is the register file which is closest to your processing element, right? And this is your SRAM cache and this is your DRAM. And what we see here is a bar chart relative to a 32-bit operation. So it's just showing you how much more expensive memory accesses are when compared to the operations. But this is, like showing you the relative cost rather than the absolute, which we had in the previous slide. Again, this is also from the same analysis from the same group a year later from Song Han and Bill Daly. And this is the reference for it. You can go and look up this paper. Yeah. So, are we sold out on energy yet? Yeah? Okay. So now, let's look at the next metric, memory bandwidth. So let's see why memory do I need to motivate memory bandwidth is important, or are we already know how important memory bandwidth is? We already know, right? If you look at the size of the AI models, the way they are going and how much data we need to pull into the system. So memory bandwidth is data transfer rate, right? So gigabytes per second. And what we see here is that we are choked by this off-chip link, which is the memory bandwidth bottleneck. Now, say we do processing in memory, how are we increasing it is because now instead of being referred to this very narrow off-chip link, we can actually put logic all the way inside these RAM chips, right? And how much we get, like 1000x increase in your memory bandwidth, right? Because now we are not bottlenecked by this serial link or parallel link, right? It's a parallel link, DDR is a parallel link. But we are directly embedding compute elements here, so we have direct access, and so you increase 100x, 1000x increase in the bandwidth. Yeah.
But in this picture, if you have something like an element-wise operation,
Mm-hmm.
do you save anything on memory bandwidth? still have to read back the data?
No, you don't have to read that data. Suppose you have an element-wise operation. That's actually a very good kernel for PIM. So before you would have to read, let's say you had like, I don't know, maybe 100 kilobyte size of the vectors. So before you would have to read 300 kilobytes all to the processor, right? The result, yeah, right, A plus B plus C, let's say, right? But here, if you do PIM, you don't have to read all of that data in. You just directly read it out from the banks and do the compute here. So you save all that data transfer. Yeah, so yeah, that's right. So if you have to, only the output, only the temporary results need to go, not the inputs. So that's what you save, yeah. And also, while you are doing, so that's one thing is how much data transfer you saved, but the very important thing which I want you to emphasize on is, while you are doing computing, you have access to this enormous bandwidth. It's not just how much you save to the host. That is a good thing. But while you're doing computing inside the memory, suddenly you have 1000x more memory bandwidth, right? So you can do all these data, access it in parallel and do it together. Yeah? So one example I love to show, now this is not PIM, okay? This is not PIM, but TPU, Tensor Processing Unit, it's Google's AI accelerator, right? So what they did an analysis in there, this is an analysis they did, and then I found it on a blog article, was that they, just by changing from a low bandwidth memory interface to a high bandwidth HBM, they got a 200x performance per watt increase in their TPU first generation to second generation. So that's how powerful memory bandwidth is, right? And if you look at the subsequent generations, so this is again, I'm cautioning, this is no PIM, they have not done processing in memory, but just increasing the memory bandwidth gives them so much more benefit. And as you look at the memory bandwidth over the TPU generations, how they have gone from 34 gigabytes per second to 1200 gigabytes per second, about terabytes, about a terabyte per second, right? So you can see that memory bandwidth is very useful. And there are many ways to go about memory bandwidth. We can do very expensive, fancy parallel links between the accelerator or the CPU and the memory, or you can do PIM, right? Yeah.
Can you explain what this memory bandwidth means? It's like, you're saying that they were doing some of the computation in some memory, right?
They were not doing computation in memory. So what it means is the data transfer rate. So how many bytes per second can you transfer, the rate at which you can transfer data between memory and the compute is the memory bandwidth. Okay, that makes sense? So before, they had a very slow data transfer rate. So they were choked at memory bandwidth, right? They were slow, they were just waiting for data to come to them. And the utilization was very poor for the chip, for the compute chip. As they started going towards more high bandwidth memory interfaces like 3D memories and all that, they could suddenly see a pretty good boost in their performance improvement. But they didn't do any PIM. They didn't do compute near memory or in memory. This was just raw, good, expensive, high bandwidth memory interface links. Yeah. But imagine how much better it could go with PIM, right? That's the next order of magnitude. Yeah. Right. And this is for the Google's machine learning workloads and machine learning accelerator. There's another academic work which I'll talk about in, I think in lecture 4, I'm going to look at this. This work came out of a group in KAIST and ETH, I think, yeah. But they mapped graph workloads to a 3D PIM solution, and they were showing, right, so this is your conventional DDR3 memory bandwidth, right, about 80 gigabytes. So this is your memory bandwidth which you can extract after you do PIM. So how much it goes up. So this, if you have a core, out of order core attached with DDR3, okay, then from there if you go to something like HMC, which is a 3D memory, no in or near memory, you get about 3x improvement in bandwidth, and then boom, if you do something compute like a processing near memory, then it goes to terabytes per second. And this is a bit old paper, right? So these numbers are outdated. With new DDR5 and so on, it would be different. But the trend, the relative trend is what you have to see here, right? Just by extracting all the bank level parallelism inside the 3D system. And we look into more detail into this architecture, but I just wanted to show you how much memory bandwidth you can improve by doing a PIM architecture. Yeah.
How complex are the operations that we are embedding in the memory?
Very simple. These are graph, this is for a graph workload. So,
and is there room for like embedding more complex instructions into the memory?
yeah, that's a very good question. So there's a limited power budget there, right? Because, you know, yeah, especially if you do 3D, there are thermal constraints there. So you have to play around with that. So that's a trade-off. With the GPU, you know, you can put in all that flops and they have a nice fancy cooling system. With near memory, in memory, you've got to be careful with that. So you know, it's not magic. It gives you all these benefits, but it has constraints too. So right now I'm motivating it. We'll get to the constraints later. But yeah, right? Yeah.
It was a detail about that research paper. I just wonder if this they have a product or just play with the simulation.
So this is a simulator paper, but there are products on PIM, which I'm going to talk about. They're actual products. Yeah. Well, I would say they're not still in the market, but they are from Samsung and SK Hynix, and they have built products, and we'll talk about that too. No, this is not a product. This is an academic paper. This is an ISCA 2015 paper. Yeah. But we have products which we'll discuss later. Yeah. Okay. All right. So far we did energy and bandwidth, right? There's one more very important aspect to near and in-memory processing, which is area. So let's take a look at that. Okay. So if you look at the silicon area occupied by the memory subsystem, you know, just in the processor, whether it's a CPU or GPU, almost a lot of the chip is cache, right? And it's becoming more and more cache. I mean, have you seen the latest AMD processors, Milan X? They have got some 700 megabytes or a gigabyte of cache. It's a 3D cache. It's amazing. So a lot of the silicon die area is dedicated to this temporary storage, right? And if we consider the whole system, this is how it looks. 10% is compute, 90% is passive memories, right? So all that silicon there is just lying storing data and not being used for compute. What in-memory computing can do is convert this passive memory into an active compute area. So it can utilize all that silicon area for computing. So that is also a very important advantage of near and in-memory computing, right? So we saw energy, bandwidth, but never forget area. Area is also a very nice advantage of near and in-memory computing, right? Yes? DRAM access is what?
I mean, cannot be saved or cannot be.
Yeah, yeah. You can use DRAM for it, but you still have to access the DRAM arrays and banks, right? So think about it when you're doing a in or near memory computing operation, just an addition, right? You have to first access A, B, do some mixed signal processing on it, write back C. So you still have to access the memory. Even with SRAM, with everything memory accesses you still have to do. For in-memory as well. And we'll see how. In fact, unfortunately, in-memory even increases the number of memory accesses. Because sometimes because you have to do bit serial arithmetic or you have to do majority function, so that increases the number of times you have to access memory to do that operation, and we'll learn about that. But how about this? By the end of our lecture, why don't you count the number of memory accesses we increased within memory? That would be a homework for us. How about that, right? Let's do that for the different things we learned about. But all the communication energy is saved, right? And the area is saved, bandwidth is saved. There are other good things about it. Yeah. Sure. Yeah.
So this one, making this more active,
Yeah.
essentially, do you mean to equip also caches with processing elements, or you mean just the DRAM?
Both.
Both.
Yeah. In caches, it's repurposed to become processing elements. So it's more like a in SRAM technology. That's what we'll learn. For DRAMs, we add processing elements and also do in DRAM. We look at both flavors. Cool. Yeah, great. I like you all. You make it so interactive and fun for me. I'm going to enjoy this week. All right. All right. So another thing is like, how do we integrate this technology into our memory hierarchy, right? So, and this is important because as you go on and do your research, you have to pick one of these, right? For industry also, you have to pick one of these. So let's look at the different flavors. So this is a no in-memory, no near-memory solution, right? So we are all good. There's no intelligence in memory. One option is go the GPU style, integrate a separate discrete accelerator through PCIe. Okay? Here, this is useful only if your raw in-memory computing is so much more efficient that you see all the benefits. But in this solution, do you save bandwidth? No. Do you save, let's see, do you save energy of data movement? No. So this is just raw efficiency of a very novel in-memory technology. So think about memristors, analog computing, this is the way to go, right? This is a more traditional in-memory hierarchy, where what you do is you take pieces of your memory hierarchy, some of the cache, some of the DRAM, some of the storage, and then you repurpose them with compute elements and use them on the fly. This will give you all the three benefits which we talked about. But this is also throwing all the problem on the software, right? This is a lot more challenging to program, lot more challenging to use. So that's the easy way out. This is the hard way. This is where all your research problems lie, right? This is what you should work on. This is leave it to the circuit guys. That's how I think of it, right? They'll come up with fancy circuits, build these chips. As architects and system designers, we should focus on that. Yeah.
Don't you need to add a layer somewhere because you need someone must manage
Managing all this, yeah. The operating system, there has to be a language feature, dynamic runtime, yeah. So that one is a lot more tricky. And also think about cache, right? It's not even exposed to the ISA. It's right. We don't know where the data goes into the cache, do we? It's completely transparent in the hardware. So now if you want to do that kind of thing, you have to expose it or you have to figure out some way to abstract it. So yeah, this is a lot more challenging.
Yeah, I'm trying to understand the complete picture. So I'm really waiting for your examples, but
You are waiting for the solutions.
Processor to just.
What is that?
So don't you need one extra processor or chip somewhere that is administrating this system here with in-memory computing?
Well, not an extra processor, but yeah, we do need some language features and operating system management, right? So for instance, for the cache, let's look at cache, right? You can use cache way partitioning to kind of partition the cache, and then few ways which you dedicate for this can become a scratch pad which is managed by the runtime.
But you still need some processing element that is doing a work here.
Yes.
Yeah.
Yes, we do need that, and we'll see how that looks like.
Okay.
Yeah, it's lots of tiny bit serial ALUs is what we have there. Yeah. Okay. Yeah.
Yeah, I think this picture to the right is quite interesting because you also show that you're taking up part of your cache and your DRAM to put these integrated accelerators. So assuming we just stay at the same area, how much capacity would you lose in your cache and your DRAM?
Yeah, no, that's a very, very good question, right? So you're right, getting to the heart of it. So I will answer your question in two parts. First, when you're not using the PIM, right? So, and the answer is different, depends on which memory technology, but let's start with SRAM's cache. When you're not using it in a compute mode, it can just act as a normal cache. So you're not losing any memory there. But when you're using it in a compute mode, think of it like it is morphed into an accelerator. That's when you are losing half of the cache capacity, it's being used for acceleration, right? You throw a kernel at it like a GPU and it accelerates it. How much density you lose by adding the compute depends on what technology you choose. So for SRAMs, we lose about 7% of the area when we do this bit serial computing. I'll show you that. So it's very low. For DRAMs, it can be more high. If you change the modify the cells, and especially if you sometimes if you have to add compute elements, you can lose 20 to 30% memory density. So it's a trade-off there, right? So how much compute do you want to add? Because DRAM is technology is a slower technology. Usually if you see DRAM chips have built in older technology nodes. So the compute has to be built in lower technology nodes, and the interconnection layers which you have there are very less, like the metal layers. So therefore, adding logic to DRAM costs you more, right? So you know that's the flip side of in-memory and near-memory computing. But at least for SRAMs, you know, we have gotten it to the point that it's very low overhead in terms of area. So two answers to it. One is raw area overhead. It varies from 3 to 30% depending on the memory technology. Dynamic overhead of how much cache you can use, that I think is not a problem. Because when you are not using it in accelerator mode, you just use it as a memory. Yeah?
Okay, thank you.
Sure. Good. But we look at all those numbers in our lectures. We'll see at different things in the lectures. Yeah. All right. So let's see. So this is some examples of, like, you know, this is Mythic AI. It was a startup which tried to integrate it over a PCIe. So that was this picture on the middle picture, right? And another example of an independent accelerator which we'll study is the Micron's Automata processor, right? That also, this is a very interesting architecture. It's no longer, they're not selling it, they didn't find a good market for it, but we'll study it. It's a very cool architecture. So that was also an independent accelerator. And now coming to the precise definition in my view for in versus near, right? I was asked this question earlier in the class. So let's look at this. So to me, near memory is this. Every memory is basically a matrix of bit lines, which are columns, and rows of cells, right? For me, when logic is outside that memory array, that's near memory for me. It has to be outside the memory array. Now, where outside the memory array, there's a lot of choice. It could be near a bank, it could be at the memory controllers, it could be at the cache controller, it could be anywhere, but if it's outside, it's near memory for me. Make sense? Yeah?
Yeah, it makes sense, absolutely, but
yeah.
You're like blocking the memory.
Yeah. You're what?
You're like blocking the memory from the main CPU here.
Yeah.
If that wants to use the memory, maybe you can't access it because you need to have a more fancy interface to the memory so you can have multiple users at the same time.
Yeah, no, you can't have multiple. Yeah, you're locking the memory, unfortunately. All the solutions we'll see, when you are doing compute, you cannot use it by your CPU. Right, so we are locking the memory. But think about it this way, right? For that short, brief period of time, it's becoming a very fast accelerator.
Yeah, of course, yeah.
Yeah, so you are locking, but then CPU can do other things, right? While we are accelerating it here.
That is a trick here. Yeah,
that is the trick. That is the trick here. Yeah, that is the trick. Absolutely right. So this is our near memory, right? Now let's look at in memory. So to me, in memory is when you are trying to do computation on the bit lines or inside the array by doing charge sharing. That's in memory for me, right? Now everybody will have different definitions and we are still converging to something in the community, but this is to me a very clean semantics, right? Whether it's inside the memory array or outside.
That's probably a bad idea, I would say.
This one?
Yeah.
Why?
For testing purposes, you are having memory bits and things like that, and now you are blurring it up with having logic inside that. So all the algorithms we're using for testing those error-prone memory areas will be more difficult. That's what I can see in front of me.
If you are actually adding logic, but you are not really adding logic, this is really charge sharing. I'll show you. So you're not really changing the bit cells. You're not adding any ALUs inside it.
Okay, so you can still make like a wrapper around the memory area and running your memory bits on that one without having to care about this logic.
Yeah, no, this logic is just, and I'll show you exactly how this logic works, but it's not modifying the memory at all. The BIST would still work exactly the way it should work.
Okay.
Yeah.
So you have a bus basically between the memory area and this computing BL.
Actually, it's not even a logic. Just hold on, you'll see how this works. It's almost magical when you see it for the first time. But yeah, this is no ALU. This is just charge sharing. We'll hold on to this. How this works, I'll show you. Okay, but it's not complicating your bit cells. It's not changing the memory at all. It's just when you open up two rows together, over the columns, you share that value, and that's how you can do logical operations. That's how it works, but we'll see. And I would like to see your reaction when I show you how it works. All right. Bit line. Yeah, so the vertical is bit line and the horizontal are rows. Okay? Right, does that answer your question about the precise demarcation? Yeah, okay.
Yeah, not in detail, but overall.
Yeah, we have a whole lecture. Right, we have a whole lecture understanding bit line computing, so we'll get there. Yeah, yeah.
In the first example, in the near memory, are we reading one word at a time or
One word at a time.
one word?
Yeah, and in the second one, we'll actually open up two rows at a time. Yeah. Yes. Systolic array, not really. We can, at least whatever architectures I have seen are mostly like data parallel. But you can build a systolic array with memory arrays, but that would be like an independent accelerator, right? I was showing you integrated, because integrated memory hierarchy, so systolic arrays would need specialized interconnect, and the current memory hierarchy has buses and rings and H trees, so they won't support that systolic movement. Right? But that would be a nice research project. One of my students actually, I think I have that reference in one of the later lectures, but they have looked at how to build a systolic array out of memory arrays. Yeah, cool. Good question. Yeah.
So regarding the first solution, thing is that, we will have block memory access, but if we have dual ports, for example, SRAM,
Yeah.
and we want to, for example, to increase the performance.
Yeah, yeah.
There will definitely be some power, increase.
Yeah,
But
yeah.
do you have any kind of studies that, for example, kind of?
Yeah, we do. We'll look into one whole lecture for that. We'll look into how do we do it dual port, what's the power implication, what's the area implication, all that. Yeah. How do we do the arithmetic with it? Yeah, sure. Okay, so that's near memory, in memory, right? And this, how you do near memory, as I said, there are lots of different, you could put logic outside the banks, you could put it next to the memory arrays, you could put it at the buffers. There's a lot of flavors for the near memory. That's why for near memory, I wanted to show you like a lot of choices are available here, right? In memory, not much, right, in the memory array, right? So that's kind of more constrained there. Okay. So now that we know the near versus in precise terminology, as a group, I'll show you the solutions, but can you identify the problems with near and in memory architectures? Let's look at in memory. What do you think could be a very difficult architectural problem with in memory? Any thoughts? Think about it for a minute. Yes? You synchronize it if they are all going in parallel. Wonderful. I say don't synchronize. Go the CUDA way. Right? No barriers, nothing, just everything goes parallel. Very good. Okay. Any more?
So the other one is with the in-memory. If you're like, you have a dedicated logic for every block, that means based on the law of large numbers, for every block you have one, let's say, a tiny processing element, therefore you're using more area.
You're more for the in memory, yeah, different flavors. You might, it depends on how you develop the technology. For SRAMs, usually we have figured out a way for very less area overhead, and I'll show you that. For DRAMs, unfortunately, it does take up a lot of area. So yeah, area overhead is definitely there.
Yeah.
very good for in-memory, yeah.
For the coarse grain, at least for the coarse grain, you don't like,
You
have
can
to share the
amortize
logic
between the
all
different
logic.
arrays, yeah.
The logic should be shared among all the blocks.
All the blocks. So there you reduce the area overheads of the logic.
And
Yeah.
But this, as you, I don't know anything about software, but this might again cause something on the software guys.
Of course. Software guys have a lot of pain points. Yeah, when logic is active, you can't use the software. And there's one more software problem. Yeah, I see a raised hands. Let's see.
So you increase, I think, in memory, increase the sensing margin.
Pardon me, could you repeat that?
Sensing margin, I mean, earlier you were just differentiating 0 and 1.
Yeah.
Now maybe more levels, so.
Right, absolutely right. So if you want to do analog computing, you might have to add ADCs, analog to digital converters there, depending on some memory technologies like memristors need ADCs. And guess what, guys? 80% of energy goes in ADCs. It's very expensive.
What do you mean with analog here? Because, I mean, you have a
Yeah, let me.
digital memory, so what do you mean?
Yeah, analog is like, let's see, I do have a, yeah, here, it's coming up. But there's a flavor of in-memory computing with memristors, memristive memories, where basically you can think of each memory bit cell as a resistive cell, and using Kirchhoff's law, you can do analog dot products. So this example is showing that. I'll jump back to that slide for the whole class, but I just wanted to show you this also. It's a flavor of in-memory computing. What you do is you send the current in, like you first of all divide the inputs into bits. Then for each bit you send a current in, right? This cell here, you know, there's a voltage, the bit cell basically does a voltage difference here, and when you sum up the current, you get a dot product of the stored bit cells. So that's the analog computing which I'm talking about. People have shown that this is very useful for CNNs with memristive technology, because you can do a one cycle dot product, right? One memory cycle. But this is very fancy, very speculative, right? It's not, as you said, conventional computers have all digital memory. It's all SRAM, DRAM. This is the next generation. They're still, these don't exist. Well, they're starting to sell memristor macros for embedded systems, but they don't exist in production systems today, right? So this is more like a research, proposal.
With a very limited amount of operations that you do, and anything that creates a carry in some sense, you're out, right? So
No, I will show you how to do carry on this. It's coming up. You can do a lot more, but this is the basic idea, right? The Kirchhoff's law and the dot product. Yeah.
What about accuracy? Is it as accurate as traditional?
It is, yeah. If you can tune the ADCs properly, then you can get the right accuracy. But there's process variation, there are other problems, but you can get the right accuracy for a dot product with accurate ADCs and DACs. Yeah, good question. Okay, so this is, I'll come back to this, but I just wanted to show this is kind of one of the analog memory concepts. So, but back to this, we are looking at the challenges, right? I told you all like glow, like happy stories about in-near. Now to this slide, I want to bring out the challenges. So we talked about area as a challenge, right? Memory density, barriers and synchronizations. Anything else comes to your mind? With in memory or near memory? Yeah.
Could there be issues with correctness of bit flipping and things like that?
Yeah, process variation, right? And like data can get corrupted if there's process variation, so you have to really fine tune your sense amps and your peripherals for that. But for SRAMs, for instance, we prototyped chips and we showed that there's 6 sigma robustness, at least. So SRAMs, it's a lot more stable. DRAMs also people have shown it can be stable, right? So that is a standing issue, but it is not a showstopper, but it is an important issue to be addressed. Yeah, and you have to kind of take extra care in the circuit to kind of make sure that doesn't happen. Yeah. But yes.
The wires that we use, right, for the split time. So probably the capacity of the wire to handle more current, that should change the cell area.
It will, yeah, especially for the analog, like the memristors and all, you have to be very careful with the bit pre-charging and bit line. But if you're doing if you're doing 2 rows, I think you don't need to change anything, right? Like the conventional pre-charging sensams would work. Yeah. Yes, absolutely. Because the wire resistance also starts adding in, right? So that can cause the, yeah, there's a lot of issues there too. Yeah. So it's a huge challenge for the circuit folks, I think, to make all this work. Yeah, there's a hand there.
Destructive operations.
Destructive operations, yes.
So destroyed when we compute something. So if he still needs input, we need to copy that.
Yeah.
For that, or we need, well,
Yeah, very clever insight. But for which one? Would it be for SRAM, DRAMs, bitline, analog? It would be the case, and for DRAMs. Not for SRAM or memristors. Yeah.
Right now we're always acting on one bit line for each operation.
Yeah.
We have an operation that covers a range. So let's say we have like a window that we are interested in for our operation. That might be distributed value across the.
Yes, right. That's absolute. That's the heart of in-memory computing problem, right? So what you pointed out, what I refer to as operand locality. Okay. So pay attention here, class. So that's the biggest architectural difference between near and in. If you look here, logic is outside the memory arrays. So this logic can grab data from any of the memory arrays, right? So you have a lot of freedom. If you look at this here, what are the 2 operands we are working on? The blue dot and the red dot. It has to be in a very specific spot in the memory array, and there are thousands of memory arrays. So how do you align the data so that you can do the operations at the correct time is a big compiler and software problem, right? Make sense? So I want you to think of a solution for it, right? I'll show you some solutions, but they are not the best, so come up with better solutions, right? Yeah.
I mean, they would be crying probably.
They will be crying, but there are clever ways to get around it, and I'll show you. I'll show you 2 compilers. Okay. Yeah, 2 in-memory compilers. They will be crying. I like that word. Okay, any more? Any more things, thoughts from the class? Any other challenges you can think of? I think we covered pretty much everything. Density, area, alignment, operand locality, right?
I can think about one more challenge is it's not between near and in memory, but it's more of a how to make a decision whether to go with this one or that one. That might be.
Yeah, yeah. You know, that decision I feel like is a very interesting open research problem. There are not much solutions for that because they're like, we are still developing all these technologies, right? So no researcher has actually thought of this very holistically, like, okay, there's so many memory technologies, in is possible, near is possible, what makes sense for what application? So that's completely open at this point. I haven't seen much papers on it.
Yeah, and again, I'm really curious to see how complex the logic is there.
Yeah, coming up, all of that is coming up. Yes, I saw a raised hand. Yeah, go for it. Could you just repeat it? Sorry, I didn't hear you.
Deciding where we want to do something, whether we want to just like move the data to the core
Yeah.
and fast forward or into memory, latency becomes a problem because now, like our memory latency, memory sizes are a lot slower than ours.
Yeah, absolutely right. So we will solve the data movement between the CPU and memory. Now we have introduced data movement within the memory, right? Now we have to kind of lay out the data inside the memory nicely and all that. But you know, it depends on which application you're solving. If you have data parallel applications, they just work beautifully, right? They can just go on parallel lanes. So there you don't have to do all that scatter, gather and all that shuffling. But if you have a browser, I don't think we should run it on PIM, okay? So that's more regular applications, and some structured sparse applications are a good fit for PIM so far in my view. But maybe the next generation, which is you all, come up with more interesting use cases. So we'll see that. Yeah. Okay. So yeah, we looked. So I just, you know, when I was showing the bit line, I just wanted to show you this form of analog computing also, which is a very, it's not a new in research. In research, this was proposed in 2015, but it is there's no product or no like commercial adoption of it because people are still grappling with the circuits and the robustness and the process variation issues with this kind of technology, right? But it's with new upcoming memory technologies. So let's take a look at the different ones we have here, right? So for instance, we are familiar with SRAM, right? But there are some new upcoming memory technologies which are multi-level, okay, and which are two properties which distinguish them is that they're non-volatile, so they're very stable, and they are multi-level. And they all are not, SRAM is like purely CMOS, right? So it's very easy to manufacture and integrate with the compute. But all these technologies, they still are figuring out how to make a very efficient process for integration with the mainstream technology. Now, I'm not a circuits person, I'm an architect, but what I get from these technologies is that they're very promising and they're still under research, right? So, but the cool fact about these new technologies is that they allow this very efficient dot product, single cycle dot product among the memory bit cells. And I was just showing it before, but imagine this is a memory array, right? This is an abstraction of memory array where each bit cell is a resistor, okay, which is storing some value. So the value which we are used to is 0 or 1 in SRAMs and DRAMs, right? Here it's no longer a 0 or 1, it's a resistance value. That's how you're storing it. And so now let's say you want to do a dot product. So let's look at the input data x and the neuron weights here matrix. So let's just look at YA, okay? If you look at, or let's see, which one am I showing in the slide? Or YC, one dot product. We are multiplying one row x with one column c here, right? So what we can see is that x can be applied as an input voltage, right? And that there's that voltage which causes a proportional current, a current proportional to the resistive value which is stored. And once you add up the current, you get the dot product out from the ADC. So this is the most common form of analog computing which has been proposed with memories, right? This is a basic dot product engine which people have shown to be very effective for what? Machine learning, right? Right? So that's the whole market, like there's a lot of startups in this area, but I'm yet to see a very robust solution here. Like Mythic AI was trying to do this with Flash, and they are still struggling, to build very robust products and so on. But yeah, this is also like, if anybody here from circuits background, or yeah, one of you, yeah. So this is a problem for you guys, Make it work for like all the different memory technologies like FE RAMs, STT RAMs, then that's a very promising area. Yeah.
But isn't IBM very close to doing that?
What is that? Yes, IBM. They're not just IBM. A lot of academics, many folks are looking into it. But
because they keep publishing on memory storage.
Absolutely, yeah. IBM is looking into it. We have people at Michigan looking into it, where I'm from. So it's an open research area, yeah, but nobody has shown a very robust solution yet. At least that's, in my opinion. I may be wrong here. Yeah, go for it.
I think IBM has shown this Thomas chip. Actually, I'm from IBM.
Oh, okay, cool. All right, so we have an insider here, yeah.
We work on PCNs and
Yeah. Does it scale? Like, can you do it in a mass?
yeah, so in 2020 we fabricated a chip in 14 nanometer.
Okay, that's good. Yeah, 14 nanometer is pretty low node. That's great. Yeah, yeah, and mass manufacturing is, again, you have to figure out all the make it a low cost process to manufacture it, right? That's
It was very expensive, that's why.
yeah, but it's an open research problem. I'm pretty sure in 5-10 years we'll have a solution there too. But yeah, I mean, I think that's the next frontier for Moore's law too, right? Like, if we can make these kind of exotic technologies more cheap to manufacture and reliable, then yeah.
The problem is the variation that
Yeah, yeah. So it produces, every chip produces a different result, right? So you have to retrain every memory array again, right? Yeah. Good. Great. So we'll look a little bit into this too, but if we have time, it's all time management, which I see that we have only 12 minutes left. Okay. All right. So, this is kind of giving you some comparison of near versus in memory among different metrics. And so what I'm not going to go over this whole table. You can look at it offline. But what I wanted to emphasize was the metrics, right? First metric is very important, cell modification. If you are a memory person, this is your number one criteria. You don't want to change the cells too much, right? Because they are very standard compilers, the memory density is a big deal for them. So a technology which doesn't change the cell is more attractive to the memory manufacturers. Cell, when I say, is the cell which stores the bit, right? Then we have density, peripheral modification. If you don't do it, you don't get anything, right? So peripheral modification, I feel, is like a necessary evil, right? So you have to do that. Now, the extent to which you do it is the question. If you are doing with in-memory peripheral, which is digital, the changes to peripherals are small. But for analog, you have to add ADCs, and that's hard, right? Then we have memory bandwidth, which technology provides more bandwidth. If you look at this, now this row is very interesting for memory bandwidth, because that's where you can see the difference between near and in memory. Near memory has, so there's no PIM, there's low memory bandwidth. Near memory increases it, but in memory just takes it to the roof, right? So if you're bottlenecked with memory bandwidth, what would you pick? In memory, right? If you can afford it, if you can build it. When it comes to energy, again, it's a lower energy. Well, I mean, it's debatable, Yeah, because some of the analog in memory can take up quite a bit of energy due to the data conversion, but it is still quite low. Now let's take a look at since we are running out of time. Another interesting thing I want to point out is computation latency. So this is, if you look at this, computation latency for near memory is actually lowest. So you get low bandwidth, but you get very low computation latency because you are integrating conventional ALUs outside the memory array, right? So it can be very fast. The number of cycles per operation can be 1 or 2. But if you look at in memory, it can start becoming high, because you have to do more memory accesses, you have to do bit serial processing and so on. So keep this metric in mind as we go over all the technology. So this is an interesting metric. And then the other one which is very interesting is precision flexibility. Most of the in-memory architectures, although their computation latency is very high, they have a lot of flexibility in precision. You can do 2-bit arithmetic, 3-bit arithmetic, 4, 7, all odd numbers, right? As long as your compiler can actually take advantage of it. That's the bottleneck there, but the hardware supports it. And reliability and ECC support, that's an unsolved problem, most of it. And the baseline has very good reliability support. So if you're a new grad student trying to find a problem with in-memory, I would say this is a very open problem. There's no solutions yet, and it's a very hard problem. So I don't know if you can solve it, but that's an open problem. And I don't think to date people have figured out an ECC which works precisely for in-memory computing. And when we learn the technology, we will see why that's such a hard problem, right? So usually you end up doing like scrubbing or some kind of other reliability support here, right, rather than ECC. Okay, so this should be there. So to summarize, let's see, how much time do we have? We have 7 minutes. Okay, I'll try to cover as much as possible. But to summarize, we have integrated with memory and independent accelerators. We have lots of different technologies where we can do this, right? DRAM, SRAM, SSD. We have near versus in, mixed signal, analog, there's a whole spectrum. And we are going to touch on most of the spectrum in our class, okay, all of it, except storage. I'm not going to do storage, I won't have time to cover storage, but everything else we are going to touch, okay, all right. So next I'm going to wrap up today's lecture. We have a few minutes with a little bit of history, and then we'll move on to the next lecture tomorrow. So this is processing in memory, as you will. The first work for processing in memory came out in 1969. Okay, so it's very old idea. But as we have moved over the years, the technology has kept shifting, and I'll show you the changes which has happened. But in 1969, they proposed, this is very interesting. So they went very deep. With every memory cell, they integrated a majority gate. Majority gate is a universal gate. And once you have a majority gate, you can do pretty much everything, right? So that was the very first paper, if we date it back, which talked about in-memory computing. This is in-memory computing. I mean, I don't know, we can call it in, but I call it in because you see this is an array of bit cells, right? So it's not the memory architectures we are used to today, but that was one of the first papers, which majority gate integration. And then in 1970, there was a paper by Harold Stone, which proposed the more conventional near memory processing, which we are used to today, like add some logic to DRAM layers. And if you have time, I would encourage you to, there are a lot more things which you should read, but it would be nice to read this very first paper, like just as a historical perspective into this. This is one of my favorite papers, one of my works later kind of takes inspiration, or well, we did that research project first and then realized it's similar to this later. But this is TerraSys system. This had a 128 KB SRAM, and then outside the memory array, they had bit serial ALUs, which would do a bit serial processing near SRAM, okay? And they could do sorting, arithmetic, lots of other operations. So this was one of the 1990s, this came out, TerraSys PIM, very cool, and this is SIMD architecture. So one of the first SIMD bit serial architectures which came out. Around the same time, there was this search memory kind of, if you want to search keywords in memory, then they just proposed like an associative, not a CAM, but more like a comparator which would be integrated with RAMs to do search in memory. So this was called like application Linda in memory. And one thing interesting, so this was SIMD architecture, and this was actually a VLIW PIM architecture, right? And it was 60x faster than the, a compute card, which was the state of art then, right? So this was in 1990s, the search in memory architecture. A more famous one is the DIVA architecture here. This one is closer to the, the PIM products which we are selling or are in the market today. They didn't really change the DIMM itself, right? Like this was a conventional motherboard and they had the memory, and they added some logic cores, not vector units, but more logic cores close to memory, right, in the motherboard. And they went after also very, one thing interesting was they didn't do SIMD, they didn't go after parallel workloads, they went after sparse workloads and pointer chasing and irregular workloads. That was the focus of DIVA, right? So that was one of the first works which tried to look at irregular data workloads with PIM processing. Yeah. Was a compiler? Well, for DIVA, I think they did have a software stack, but not for TerraSys. Yeah, not for each of them, yeah. But I'll show you a lot of compilers. My own group has developed compilers for these, so we'll look at that, yeah. This one is the most famous one, the IRAM architecture, the intelligent architectures from Berkeley. And they did, this was one of the first PIM solutions. So these are the DRAM these are the RAM chips here, and they added actually vector processing units back then in 90s to the RAM, right. So, one of the things which they discovered, this papers, that of course it sped up things, but it cost a lot of area. This was the first paper to show that how memory density can be impacted if you add logic to the RAMs. Yeah, so this they had only 13 megabytes in the DRAM in 8 banks. It was a very, compared to today's gigabytes of RAMs, is a very old technology and architecture. And then the final one, which I'll do today, from the old history times, is a very interesting architecture called the traveling threadlets, right. So, we saw SIMD, 2 SIMD architectures and 1 DIVA, which was for irregular workloads, right. How many here know what is regular versus irregular SIMD? Can you raise your hands? Very few, okay, all right. So, maybe I'll just show you a slide on what I mean by those terms before we start the next lecture, but this is interesting because here I told you there's a problem of memory data mapping, right. You have to go and map the data in the right location in the memory to do the compute. They solve this problem by migrating the compute threads with the context. So, a thread would migrate from one memory chip to another memory chip, follow the data around. How does that sound? Nothing of what we know today, right? Because now we just run the thread on a core, grabs the data and does the computation. So, data comes to the compute. Here, the compute context is migrating among memory chips. So, that was a very cool idea at that point, and didn't really succeed because the programming model was very complex, right, and limited applications, but a very clever and interesting research idea. So, if I were to pick 2 papers to read, I would pick this one, traveling threadlets, from the old like 70s and 90s, and the TerraSys paper. These are my 2 favorite papers to read from the very old PIM papers, right? Fun to read. You would enjoy reading them, whether they're practical or not. And that's it. We'll just, I won't be able to finish all the lecture deck today, but I'll just leave you with traveling threadlets.
Okay, that's the title of the paper. Or how do I find it?
Yeah, so this is the references here, Peter Kogi of Piglets and Threadlets. That's there on the slide, Gossamer Core, and the other one would be TerraSys, this one. These 2 I would pick, yeah, because there's so many like architectures out there, but those are the fun ones to read, okay. And so, I'll leave you with what is today. So, those were 70s and 90s, right. So, what's today is we saw initially some 3D memory, actually HMC based hybrid memory cube architectures with 3D RAM, and this purple was the logic layer. Then we saw DRAM DIMM based very interesting architecture, Micron's automata processing. I am going to teach you about it also in the class. That was for finite state automata, FSA, okay. And this one was more flexible, it could do more logic, that was a near memory, right. So, this here, the 3D is near memory, automata is in memory. Then we have got the UpMem, we are going to learn about that, it is a startup. That is also near memory, we are going to look at that in lecture 3. And we have the Samsung's HBM PIM, we are going to look at that too. So, that is another commercial example of PIM. And we have SK Hynix AIM, this is the latest one, 2022, right. So, this is the latest PIM architecture which has come out in the market. So, we are going to look at all these 3. We are going to look at automata, which is old and it's very interesting. So, I want to teach you that, but it's not in use today. They have cancelled that line, I think. And there is another Samsung ACACES. This has limited parallelism. We'll see if we can cover that. And this lot more, there's a lot of interest in PIM recently in the last 5 years from industry. That's why this field has come back alive. And there are so many more academic proposals, academic chips, right? So this is industry, there's a lot of academic proposals which we are going to go over, right?